Hello, Brad. Nice to have you on my podcast. Super happy to see you after a couple of years.
Yes, thanks for having me. It's exciting.
How have you been? You got lost
Uh, I
for a few years or a few months.
yes, I've been good. I've been very busy. I have moved to Buffalo, New York, which is not that far from well, in American terms, is pretty close to Ithaca, New York. It's about a 2 to 2.5 hour drive. Um, and I'm back in the lab, which is very exciting. I started my career in the lab, and I went to Cornell. I got a degree in molecular biology. I was very good at the lab work, but I didn't fit in with the culture. And if you go down that road, your job choices are either you go into academia or you go work for pharmaceutical companies, and neither of those roads really suited my personality. So I went into farming and I did all these other things. I became a chef um and then ultimately looped back around, and now I'm doing biology, but I'm back in the lab and I'm sort of doing it more on my terms rather than working for a pharmaceutical company. So it's great. It's exciting, and that's why have not had a big presence in social media for the last year, because I've been doing this, and it's very to get started in this is very time. I mean, it's still time intensive, um, but
Your
the
passion,
startup phase was long.
your passion, right?
So
So
yeah,
if it's your passion, then you're passionate about everything we will discuss. So I think you're doing
yeah,
good.
absolutely.
And I'm not sure if you want to say a word or not, but so the cooperation with Dr. Mercola did not work out, or you just decided to move on.
So no, that's actually ongoing, and so it's been helpful for me. I, I am being paid to develop a couple of commercial assays for him. I'm not really at liberty to say what they're going to be, but it's been fun. That's sort of allowed me to get back into the lab, get my feet wet, and get back in the game sort of. But now I am looking to expand and take over my own thing, and so that's kind of where I'm at this moment. We've got big things planned this year. Starting a podcast with Ashley Armstrong, who of Strong Sisters on Instagram. She bought my pork business a year ago, um,
Okay.
and so that was so we've sort of that's the collaboration has gone from there. So that's another thing that'll happen this year. So it's a very exciting time. It's a very exciting year, and we're looking, yeah, and I'm looking to get, like I say, back into the lab and get this thing funded and do prove a lot of these theories. Right, I have a lot of ideas. Now it's prove it time. Yeah.
So all the things that will follow now in our discussion and what you're doing in your lab or what you will be doing, um, do they emphasize or prove, let's say, all your theories around the croissant diet, the protein restriction emergence diet, or have you changed
Yeah.
views around it?
So right. So that's exactly what we're going to be doing. What we're going to be doing in the lab, we're going to use the tools that the pharmaceutical industry has built to do these kind of high throughput screening, right? They have all of these machines and equipment. Like they'll have a library of 5 million drugs, and it's all supposed to cure cancer, right? Or maybe one of them cures cancer. And so they have these ways that they can screen through all of these different things and see if it kills cancer cells, right? I want to use their tools and their machines, except instead of looking for cancer drugs, we're going to screen, you know, different types of fats, different amino acids, different levels of glucose, and see how that affects the cells. And then what we can do is we can use um, inhibitors that will inhibit a specific enzyme and say, okay, now let's inhibit this enzyme and let's run the screen again and see what happens. And we can collect just an enormous amount of data this way in a very short period of time. And we can look at things like, um, are the cells accumulating fat? Are the cells in oxidative stress? Are the cells in reductive stress? Are reactive oxygen species building up? Are lipids peroxidizing, right? We can see all these things with fluorescence stains and automatic microscopes and we can set all these up with robots now, and I can build the data pipelines with AI. So it's an exciting time. So so
So you
and
have
all this
ten.
data, all the data that we're going to generate is going to be public access, right? None of this is proprietary. This is just going to go into the public domain, and just to show, right? And then what we can do is we can do it once in human liver cells, and we can do it again in human adipose cells, and then we can put the adipose cells and the liver cells together in a plate and see what happens then. So there's a lot of ways to kind of skin this cat, as it were.
Perfect. I put myself forth if you want any. I can be a lab rat for you or anything
Yeah,
else.
yeah, yeah. Well, what's kind of neat. So you can take a skin punch biopsy. You can buy these on Amazon. They just take a little bite out of your skin, right? And in that layer of skin, there are stem cells. And so you can take from any donor, you can take a little biopsy, you break up the tissue, you can get those stem cells to grow in the lab in the dish, and then you can have them differentiate into fat cells, into adipose cells, and then you can test those. They'll almost differentiate into liver cells. They're not exactly liver cells, but they're very much like liver cells. And so you could take any individual genetics and
Yeah.
run them through the same kind of set of experiments, which is very cool. And you can do the same thing also just by collecting. If you collect blood, you can collect the monocytes, which would become the macrophages, and you could test those as well. But it takes quite a bit of blood. But I mean, not that much blood, and you could do it that way as well to see, you know, in any individual what's causing is it the amino acids that's causing the insulin resistant? Is it these kinds of questions, right? Like maybe one person is very sensitive to rising levels of branched chain amino acids. Maybe another person is very sensitive to rising, free fatty acids, and that's causing their insulin resistance. And you could see the difference. Now, that would not be a cost-effective test. That would be very expensive to run a full-on cell culture on each human being. But in theory, it's possible. But I think more what will happen is we'll be able to see the kinds of patterns of things that are causing insulin resistance or not, and then we could say, okay, well, how, when you eat, when you take certain supplements, how do we get your blood to look like the blood that doesn't cause the insulin resistance? Sort of the idea is the first step is define the components that are causing the problems, and the second step, and then you start to work backwards from there. Okay, well, if that's the problem, then how do we do X, Y, and Z, sort of.
Cool. The most people at the moment, the hype is all about the sugar diet and the honey diet. There are distinct differences. Sugar is primarily sugar, and honey is, I don't know, honey and fruit until the midday, and then a normal meal in the afternoon. So
Right.
what's your take on that? Because it's all around protein restriction. Tell me.
So one of the things that right, so we can see that in the blood there's a couple things that cause the insulin resistance, right? And one of them, without a doubt, is branched chain amino acids, right? So branched chain amino acids are in most protein sources, and it doesn't really matter if it's protein from a cow, or if it's protein from a soybean, or if it's protein from wheat, gluten. They're all rice is very high in branched chain amino acids, and so in most foods, the branched chain amino acids are 18%, something like that, 17% of the protein in the food. And what happens is when you stimulate insulin, the insulin blocks, slows down the breakdown of proteins in your body, right? And so if you're not breaking down the proteins, the branched chain amino acids in your bloodstream drop. And so when you eat sugar and you don't get any protein with it, branched chain amino acids will drop. And when that happens, that allows you to actually burn the sugar that you're eating oxidatively, right? Instead of doing glycolysis with it. And that plays into what a lot of what I've been saying on my blog recently is that you don't want your fat cells or your liver cells to be anabolic, right? Anabolic means growing, the tendency to grow rather than burn, right? You want your fat cells and your adipose or and your liver cells to be catabolic, which means you want them burning, you want them using oxygen, you want the fuel burning oxidatively. When you switch over to glycolysis, that's no longer the case. That's an anabolic mode. Cancer cells like to grow and divide, and they're very glycolytic. They're not using oxygen in their mitochondria to burn the fuel. They're tending to take in the fuel and ferment it and spit out lactic acid. And so that glycolytic state is very growthy, right? Is the term I like to use. It's very growthy. And so you don't want your fat cells to be growthy and you don't want your liver cells to be growthy, right? You want them to be catabolic. You want them to be breaking down the calories. You don't want them to be
Mm-hmm.
building stuff out of it, which in both of their cases, the things that they build out of it tends to be fat. And
Right.
so one of the things, and so when you eat sugar and you stimulate insulin, two things happen. The insulin will stop lipolysis, which is the process by which fat cells release free fatty acids, and it will block the release of the branched chain amino acids. And if you have high um, free fatty acids, or if you have high uh, branched chain amino acids, and especially if you have both, those things are both going to prevent you from being able to burn the glucose in your mitochondria, right? Both of those things sort of take priority over the glucose. Like out of all the fuels, um, the fat always goes into the mitochondria. The branched chain amino acids are always there, but the glucose is the hardest fuel. If you have metabolic syndrome, glucose is the hardest fuel to get to burn oxidatively in your mitochondria in the way that you want to, right? And so a lot of times people, right, people who have this problem, right, their free fatty acids are too high, their branched chain amino acids are too high, and those things are both blocking the glucose from burning. In those people, when you do a ketogenic diet, that can be incredibly helpful, right? Because you have this problem that you can't get the glucose to burn. And so I believe this idea of the protein, so we've done that for a while, and that works for a lot of people. But I think this idea of the sugar and the protein restriction is that it blocks both things. It will bring down the branched chain amino acids and it'll bring down the free fatty acids, and that lets the sugar that of course you're actively consuming to actually burn and to do kind of the thing that you want it to do.
And does this apply also to, so you said in a ketogenic state that is helpful, right? But in a ketogenic state, you probably will have high free fatty acids, and
Right.
you will also have potentially high branched chain amino acids, or is that the differentiator why someone might have a 60, a blood glucose of 60, just saying a number, and another might have a blood glucose of 110?
Yeah, I believe so. And so, to my knowledge, Amber O'Hearn was, I don't know if you're familiar with Amber O'Hearn, but she's a very well known in the carnivore space. She's a friend of mine, and she released a diet probably 10 years ago now that she calls KetoAF.
Mhm.
And she talks about, and that's a keto diet, but it's protein restricted. And what she says is, you take a steak with, that has a significant fat rind on it, and you eat the fat until you feel satiated, and only then do you eat any of the actual muscle meat that has the protein in it? And so KetoAF was a protein restricted keto diet um, that she was talking about 10 years ago that helped her maintain her weight. She felt like if she ate the meat that way, it allowed her to stay lean. But if she ate a lot of the protein, uh, she would start to gain weight again. That's maybe I've misquoted some of that story, but that's essentially how I understand it.
Cool. Because I've been wondering a lot about it with all the different camps about protein these days. That if you eat, you still need enough protein. So that was stated by Bart K. And that you need to eat in one meal a day enough protein in order to stimulate enough insulin, which will trigger all the processes. And there are other people which say in the same context that maybe someone is predisposed genetically and cannot elevate so much insulin. So basically, they end up maybe because they're not eating so much protein as well. They end up with higher blood glucose, and in that case, the fix in the ketogenic context would be to add some sugar, carbs, in order to stimulate insulin, and you can clear that sugar. So it's like too many, there's too many shades of gray here, right? Or
Yeah, and so there's a lot of right, there's a lot of differences between individuals, and we can see that. Another person who I collaborate with goes by X Fat Loss on on Twitter. So he recently tried the sugar diet and he gained weight on it,
Mhm.
right? And so the sugar diet clearly does not work equally for all people, right? And I think I think there's a certain type of person um yeah, where that works fine. And it looks to me like people who are mostly metabolically healthy but trying to optimize, I think for them it seems like the sugar diet can work pretty well. I think if you're someone who has been what I'm going to say is metabolically broken and has been for a long time, I suspect the sugar diet will work less well. And the the current series of articles that I'm writing on Fire in a Bottle is um, building towards that, right? I've talked a lot about what causes this growthiness, and I think it's the fact that you're not able to burn that glucose oxidatively. You're using that glucose glycolytically. You're using the glucose to generate NADPH, which is very growthy, instead of burning it. And so, in those people, maybe like you say, if you eat protein and sugar together, you'll
Mhm.
get a higher insulin release, but you're also going to release more branched chain amino acids. And
Mhm.
so now, you have this escalating battle between the insulin and the intake of the branched chain amino acids, and how is that going to come out? I think that's going to vary by individual, right?
Okay.
Individual mileage may vary, we would say.
How could, the people listening to us, what can they take out of this? Right. So obviously they need
Sure.
to test a bit, know their insulin resistance, maybe their insulin, maybe do an glucose tolerance test, or how would we summarize it?
Yeah, I mean, I think a glucose tolerance test is a really interesting thing. I think that's what, if you want to fix yourself, right? If you want to be truly metabolically fixed, you have to be able to pass a glucose tolerance test. You can sort of I do this that right that there's an official way to do it. I have uh, an at-home version of this. You can go to a drugstore and buy pure glucose cap capsules, and I forget, I think it's 75 grams of glucose that you have to consume. And then I just have I don't have a CGM. I just have the glucose monitoring system from the drugstore that you prick yourself and test. Um, and what you should see is you eat the 75 grams of glucose, and then after 2 hours, I think you want your uh,
Below 140.
blood glucose to be back below 120. I mean, I think ideally you'd be back below 100. They say 140, but I think that's really you want to be back below 100 in
Yeah.
2 hours. At the peak of so when I so I did right? So there's been a lot of protein, like as we said, ex fat loss. He does a diet where he mostly drinks heavy cream, which is another. It's similar to the keto AF diet where it's very high in fat and it's very low in protein. And that's worked for him for weight loss. I did the emergence diet, which was it was not high in sugar, it was very high in starch and very low in protein. And I lost weight on that. Ultimately, I couldn't maintain that. Uh, I couldn't maintain the low protein, not because it was not because I think it was a problem for me health wise. I just couldn't maintain it because just for palatability reasons. I couldn't just keep eating, plantains and manioc.
But you advocated in one of your earlier articles, which I really liked, about the three countries, the Chinese and the French, who
Right.
are healthy and they have a diet which is high in starch and has butter in it as well, or saturated fat.
100 years ago or 200 years ago, even more so, your diet was constrained by what you could produce on your farm, right? Most people lived on farms. Most people were farmers. If you lived in France, if you lived in the US, the engine of the farm is the dairy cow, right? Everything on the farm revolves around the dairy cow, right? That's how farms worked. Um, And so your main source of fat was butter, which is very, very saturated. And I don't think people understand how much more saturated butter fat is than steak, right? People think steak is saturated. It's not really. It's maybe 45% saturated. The butter's 70% saturated, right? And on the farm, you would kill perhaps one dairy calf a year and maybe two pigs, and that would be for the whole and that would be split through the whole family. And so the traditional farm diet is, conversely, every day the cow is generating more whole milk, and you're using that to make butter. And so, the ratio of fat you would get on the farm from dairy was probably 5 times as much as all the other sources of fat in your diet combined. And so it was a very saturated fat heavy diet. And what you ate was, and then you would grow, your wheat or your oats or your corn, right? And that would be a staple. So the staples of the diet were, or potatoes, right? Or potatoes, corn, wheat, barley, oats. And so you'd have these grains, starchy tubers, and you'd have your butter and your whole milk, right? That was the diet of America, of France, Ireland, England. Uh, Even you go into Asia, right? And the herder, like the people who live in the higher regions, Tibet and Mongolia are also, they herd yaks and sheep way up in the mountains, and they're eating, they're eating yak butter tea and noodles. You go to Africa, and there's, milk is the staple, and then they have, I forget the sorghum. Is it sorghum or teff? I forget what the grain is. It's neither of those. It's another one. But there's Africa. You see the same thing, right? And so all of these parts of the world, dairy predominated. You mixed butter with grain or potatoes, and it all worked pretty well from what we could see metabolically, right? And China is different, right? There's a lot of people in China, obviously. The farms are very small, and Chinese farms don't have room to have a dairy cow, right? And so their diet is like 85% rice, or in different places it might be 85% sweet potatoes, or in the north it might be mostly corn or mostly wheat. And those diets, which are very high in starch and low in protein and low in fat, that also worked out for them metabolically, right? Like there are problems with those diets for sure, but they were insulin sensitive, right? They weren't metabolically broken in the same way that people are now. Um, and so then over the course of the last 100 years, we've added the vegetable oils, and we've added the olive oils, and we've added all these things. And I don't think those patterns work as well. You look right now, um, Spain, they enjoy olive oil. It's one of the most diabetic countries on the planet. They're catching up with America. Italy, they enjoy olive oil. They have the highest rates of fatty liver disease on the planet, and the obesity rates in the olive oil growing regions are as high as in the U.S. So and I just don't think that these unsaturated fats pair as well with the starches as the saturated fats do. Ultimately, when you look at the full scope of time and humanity.
Okay, so starch and butter is typically not a problem if you're healthy. If you're
Right.
unhealthy, is it you lost kilos? So I guess easily as well, as far as I remember. So I think it's also a strategy. What about the sugar
Right.
diet in the context of fat as well? So because sugar higher in fructose, we target more the liver. Would there even saturated fat be a problem? Is there a kind of a red flag that goes up at the same
Yeah. So
time?
I think that sugar compared to starch there's some interesting differences, right? So sugar is more likely to stimulate this hormone called FGF21 that's released by the liver. And a lot of people think that hormone is providing a lot of the positive benefits of the sugar diet.
Mhm.
Um, whether or not that's true, I think there's evidence to support it for sure. Time will sort of tell. Um, the other thing is that the fructose does not stimulate insulin. And so, you know, uh, calorie per calorie, you're going to get more insulin from starch than you're going to get from sugar. But then the third thing is that um, there are very few sources of starch that don't provide protein as well, right? Like most of the grains are relatively high in protein. And that's why when I did the emergence diet, I was eating a lot of manioc, or also known as cassava,
Mhm.
because cassava has almost no protein in it, but it's one of the only true sources of starch that I find palatable. That is an almost pure source of starch and doesn't have a lot of protein associated with it. Potatoes are not bad. Potatoes have a lot less protein than grains do. And so so that's the whole thing, right? If you're trying to get to 5% protein, it's very difficult to do it with starches because most of the sources of starch, like if you want to eat rice, well, that's 9% protein. So there's no way to get to 5% without uh, sugar or something along those lines.
Is it so 9% out of the total calories, right? So you need to eat
Right, right,
so
right,
okay.
right.
And
And wheat is like 14%.
I'm trying to get my head around it. So do we really need to go to 5%?
Um, the Lambing lab did these studies in mice,
Mhm.
and what they showed was that they put the mice on the classic diet that causes obesity, the diet-induced obesity model, and then they removed the protein, right? And once they got the total protein down around to 5%, uh, it cured the mice of the obesity caused by the diet, right? And so that was where the 5% number came from. The mice had some advantages at 10%, but at 5%, they were like cured. They had no metabolic syndrome at that level. And so that's where the 5% number came from. Um,
And this will allow, if you can explain us, so this will allow on a cell level what will happen. So we actually reduce branched-chain amino acids on blood, but also inside the mitochondria, and allow basically the ox oxidation to resume where it's blocked. Is am I?
right, right. I mean, that is the theory. And I think between um, between Amber O'Hearn's findings with KetoAF and X fat losses finding with heavy cream and my experimentation with the emergence diet and now people having success with the sugar diet, I think, plus the results from the lambing lab in mice, there's another. I'll throw another study out there. So scallops have a very interesting. Uh, the one source of protein that is low in branched chain amino acids is collagen, right? It's very low in branched chain amino acids. It's very high in glycine. And if you look, for whatever reason, if you look at a scallop, um, the scallop has a protein composition more similar to collagen than it does to muscle meats. It's low in branched chain amino acids. It's higher in glycine. And there's another study where they most in the diet-induced obesity model, the protein source is usually casein out of milk. Casein is very high in branched chain amino acids, and they just switched out the protein source from casein to scallop protein. And so the mice were getting the same total amount of protein, but the ratio of amino acids were different, right? They were getting more glycine and they were getting less branched chain amino acids. And the scallop protein also prevented the diet-induced obesity. Um, and the Lambing Lab has also done studies where they show that specifically the insulin resistance is caused by two branched chain amino acids. It's
Isolate.
valine and isoleucine are the two culprits, right? As they narrowed it down in their search, and so it does seem like there is something to the fact that if you are in a insulin resistant state, the valine and the isoleucine are absolutely contributing to it, right? And so all these different diets and these different mouse studies are just different ways of kind of looking at um, that same problem, right? And
Yeah.
eliminating that same problem. And so, and like I say, it doesn't work the same way in everyone, right? Some people do very well on, you know, I call it the bro diet, right? It's like people who want to be like, they want to be bodybuilders and they want to be lean and they just eat like boneless, skinless chicken breasts and like egg whites, right? That diet works for some people, but it doesn't work for me. It doesn't work for a lot of people.
Yeah, because there are two different states, right? So if someone is a bodybuilder,
Hmm.
exercises, he's young and everything, and
Right,
then follows this type of diet, which I mean, it's probably not calorie restricted, but then that's a completely different state than if you take this diet and put it to someone who maybe is not exercising, who already has problems, etc., etc. So yeah,
right, right, right.
cannot compare. But about this branch in amino acids, let's keep discussing about it because the honey diet says sugar or fructose in this case for let's say 23 hours, and in the evening 7 o'clock you eat steak with some veggies, still low fat.
Right.
I'm not sure if that's important, but in any case. So, and then we have your scenario where you did the emergence diet and the croissant diet. So you lowered your protein for a while. You saw your blood glucose regulate, so everything was working fine. So how long does it actually take for the branched-chain amino acids level to 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 come down? And the second level, the question is, at which point are we saying, okay, we're fixed, and then we can maybe do a broad diet?
Yeah, well, that the last part is the hardest part, but I could the Lambing Lab, I don't have it fresh in my mind. They did a clinical trial in in adults where they restricted protein, and they showed that the levels of branched chain amino acids in their bloodstream dropped in like, I think it was within a week. It wasn't a very long clinical trial, but they showed in humans that the same thing that they see in the mice, where the BCAA levels drop, happens quite quickly. And that's what I saw when I did the emergence diet. Is that um, the my blood glucose levels dropped quite quickly, right? It only took a week or two. And then I was burning glucose and I did the oral glucose tolerance test that we just described with the 75 grams of glucose. And after 2 hours, my blood was like 66. Like I was actually hypoglycemic, which is not a thing that has been common in my adult life or ever. Right? Like my blood glucose is never low. So that was new to me. Um, and so, yeah. And so, I think it's hard to deny that there's something to um, the protein restriction for someone who is very much metabolically broken, as we'll call it. What I like to think of it is subclinical torpor, right? We talk about these animals are they need to store fat to survive winter, and I think a lot of us are in that state, right? There's a an interesting anecdote is there is a tropical primate, right? The fat-tailed dwarf lemur. So they're not monkeys, but they're quite closely related to humans. In the broad scheme of things, and they live in they live in Madagascar, and they fatten up to get through the dry season, right? And so you look at if you look at them, you can see what they're doing metabolically. Things like increased desaturase enzymes, delta 6 desaturase, SCD1. They do that and they store fat incredibly efficiently. They eat mostly fruit. So they're eating fructose. They're literally eating the sugar diet and they're fattening up for winter because that is the state that their metabolism is in. Right. And I think a lot of us are in that we've inadvertently triggered that same state, which of course all mammals to some extent can do,
Hmm.
given the right circumstances.
What do you think about the term metabolic swamp then? Because the term metabolic swamp, which you've talked about a lot actually, then it says there is a keto magic and there is a sugar magic.
Yeah, the idea of the swamp I stole from Denise Minger, but it's the idea that if you combine starch, protein, and fat, that is you know, if you are metabolically triggered by any of the three, right? We're probably all a little bit different. If you're triggered by any of the three, if you combine them all, that's probably, which is of course what we do in the American diet, or in the also in the the Western diet, we'll say, um, that's probably the worst case scenario, right? That's the hardest scenario um, to continually do well in. Now, of course, that's sort of the goal, right? Is to be able to do that. And if you look at the diet induced obesity model, the mice in the lab, um, not only is it so the macros are like 20% protein, 40% fat, 40% carbohydrate, right? So that is the swamp, right? You have almost equal amounts of the three macronutrients. And uh, also, the fat is about equal parts saturated, monounsaturated, and polyunsaturated. And so that truly is the swamp, right? Nothing is restricted. You're getting equal parts of everything. And that diet reliably fattens up the mice in the lab. And so then you think, okay, well, what can we change? Well, you can change the type of fat. You can change the amount of fat. You can change the amount of carbs. You can change the type of protein. You can change the number of proteins. You can change the type of carbs, right? And all of these things are going to have different effects. And so, you know, uh, it's a lot of combinations. Oh, and by the
Yeah,
way,
no, too
this is
many
what
levers to pull actually. But because here what I mean very uh, very in a very light way you can say okay, metabolic swamp is something that has equal amounts of carbs and fat. We'll discuss about the type of fat.
there's also evidence that in a lot of people, a very low fat diet is effective, right? It doesn't work for everyone, but there are certainly people, if you say, okay, just restrict fat, they will lose weight and they'll regain insulin sensitivity. There's other people you say just restrict protein and they will do the same. And then there's other people that you say just restrict carbs and they will do the same, right? And so all three of these systems are, you can see that all three of these systems are contributing to the problem. And it's not really right. The problem is not the swamp per se, of course. It's um, the problem is that uh, people are fundamentally broken, and we can talk about how they got that way, but they're broken in response to one of those things. There are probably genetic differences why some people are more bothered by the proteins, and some people are more bothered by the carbohydrates, and some people are more bothered by the fats. But restricting any one of those three, or even changing the type of any one of those three, um, can make significant differences to try to get you back, uh, where you need to go.
What about not mixing certain macronutrients together?
Yeah, that's interesting, right? And then it it brings up another question, of like, when you say don't mix macronutrients, do we mean like throughout the day, throughout a meal, throughout a week,
Exactly.
right?
Throughout,
Like,
I
so,
would, yeah, throughout the meal, right? So you have, so you say, I mean, I'll start my day with a juice and some fruit, and then maybe have at the end of the day some steak, or the other way around, maybe cream in the morning and then just protein in the evening. So just try to,
right,
or if you have carbs, don't have them with fat at the same meal. So yeah,
right.
as meal separate macronutrients in a meal timing, give the opportunity. Actually, let me maybe put another sentence to it. Give the opportunity to the body to use that fuel, and then maybe you eat until you actually feel a bit hungry, which means that the energy level has lowered, which means that you have probably used up, fat or carbs or whatsoever from your previous meal, and then you have a bit more liberty in terms of switching it up.
Yeah, I think that is, I think that's very sensible, right? This idea that keeping the macronutrients, separated in time and space, right? As we say in the USDA meat plant. The this no, I think that's a very smart idea. Okay, breakfast is fruit, dinner is steak, and that way you're not, right, because what you see is that when the body is lipogenic, right, when the body is making fat, when the body is in a an anabolic state, right, um it's using components of, it's using the fat you ingested. It's also using the carbohydrates that you ingested, and it's using the protein that you ingested to do this anabolic process in your liver and in your fat cells, right? And so, if you don't give it all of those three things at once, you've taken away one of the tools that the body is using to enforce uh, its state, right? I think a lot about this idea of the subclinical hibernation. Um, it's a state, right? The body has ways of maintaining state, right? It has all these feedback loops. If we think about it from that perspective, it's sensible because if you're a mammal that lives far from the equator, your biological imperative is to fatten up, right? And so it's keeping you, once you're in that state, there are all feedback loops that are trying to keep you there. And one of the ways of breaking that cycle is by not giving it all of the different macronutrients in one sitting. Like I say, the branched chain amino acids, if that's the issue, they don't necessarily fall that much after a single meal without, they probably do. I mean, probably having a very low protein meal does lower branched chain amino acids, but they're lowered more significantly if you restrict protein for, a week rather than if you restrict protein for a meal. And so
Yeah.
it also just sort of comes down to how broken are you, um, how much do you need to restrict, and questions like this. But I do think there probably is advantages to meal going one way or the other.
So that's why some people also recommend that you need to watch the scale. So actually see kind of the result, right? So I think in this case there would be two results. One is lower blood glucose, the other one is that you actually lose kilos, right? If these things
Right,
don't
right, right.
happen, probably you need to adjust. I'm a believer of a high metabolic rate. I am
Right.
convinced of that also for myself because I've seen my metabolic rate going higher by eating more, etc. And I see it also with
Mm.
a lot of ladies who try to restrict calories, run more, and they get stuck and they cannot lose kilos. So But so all this discussion we're having, I think, are we having it in a calorie sufficient context, or should we, some people reduce calories?
Yeah, so right, so calories are a very um interesting thing. I believe that a metabolically healthy person uh should eat a lot of calories, right? Like the goal should be, um, there's evidence, and I posted on my blog from the 1939 USDA Yearbook of Agriculture. They have a long article about what people eat in the United States. It's on my blog. It's up in the
Yeah, yeah.
top menu bar. You can pull it down, and so that showed that the wealthiest Americans, or the wealthiest men in America, were presumably um, working. They're things like doctors and bankers and lawyers, right? These are not people who are out laboring in the fields, right? So they probably live. This is they probably live in an apartment, take a cab to work, sit in an office all day, and they were consuming 4,500 calories a day because they could afford to. And there was no stigma at the time about calories, right? No one was fat. People ate a lot. They ate pie for breakfast, lunch, and dinner, and that was just considered normal. And of course, you would eat pie for breakfast, lunch, and dinner if you could afford to, right? Um, and then that changed, and then the perception about calories changed, and then somewhere along the line we were like, it's about calories, but I don't think it's about calories. I think it's about the individual decisions that the cells make, right? If the cells, and if your adipose cells and if your liver cells are fundamentally in an anabolic state, they are going to grow. And trying to fight them by restricting calories is, you're not going to win that battle. You're never going to win that battle. You can't win that fight, right? You have to fix the metabolism. And so I think that when you're on the right trail, um, when you're going in the right direction, you should lose weight as calories increase, to some extent. I mean, that's the ideal scenario, is you figure out a way that you're actually consuming more, your metabolic rate is increasing, and as your metabolic rate increases, you're losing weight. That's the golden path. But it's obviously hard to thread that needle for most people for many, many reasons. Um, but that is sort of the right.
I
That's
think
that's the ideal scenario.
how I imagine it is that as you fix your metabolism, maybe you also have a bit more buffer. So in case in days that you want to restrict calories or you skip a meal, then the system keeps working. Maybe then you accelerate a bit the
But so there
loss.
one of the things I talk about in the blog, in Africa, there's a tribe that has a ceremony where a young man who wants to get married um, overeats a tremendous amount of calories. Like some of these guys are consuming 12,000 calories a day, and it's grain and it's whole milk. And they're literally just sitting, and some of them, when they start this, they'll actually puke multiple times a day because they've just stuffed themselves to this uncomfortable point, and they'll throw up, and then after a few days they get where they can handle this, and they do this in order to gain weight, because when they get a little fatter, it's a show of wealth, right? And then you walk through town and a young woman sees you and says, "Oh, that guy's nice and fat, he must be rich," and that's how you find a wife. um and what happens is, in those guys, if you come back in 2 years, inevitably they've lost every single pound, they've lost every single kilogram. 3 years later, they're the exact same weight that they were before they did the fattening ceremony. And it's not like they're trying to lose weight. There's no stigma against that in their community. In fact, it's seen as a good thing, but they just went back to normal eating, and magically the weight just fell off because they're not fundamentally broken, right? So you can use uh, calories to as a bulking tool, but it's hard. So, like if you're metabolically healthy, it's actually hard to force yourself to gain weight by overeating. You have to overeat by a tremendous amount. Um, and so, it's and then as soon as you stop, doing it, you just go right back to your normal way, right? It's actually hard to do.
I agree. So my personal experience, because I was playing around a bit with carbs. So first of all, like before a couple of years back, so I increased by weight, but mostly by muscle. I put on 3 kilos from 62 kilos, which I think was too little, went to 65 kilos. And it was pretty difficult to add kilos. So I eat ad libitum and I don't put on kilos. When I
Right,
add carbs, some rice, etc., not anything crazy. I mean, still in the keto context, so low carb. Then
right,
I did
right,
put 3 kilos on. I went to 68, and then that was in a course of months. So I guess my body was adjusting. And then in the next 1 month, by keeping the same amount and more or less the same diet, I went down to 65 again. And
right.
I think that was a positive in the sense my body adjusted, but now I'm still at that level, which is I'm still trying to experiment and see what's happening.
Yeah, it's interesting. And I mean, there's a lot of things that change, right? One of the things that when you go from a keto context to uh, consuming glucose, one of the things, of course, that happens is your glycogen stores can increase,
Yeah.
right? And that alone can account for 3 kilograms.
It could be
And that
because
is
I did feel fuller, so I mean not fatter, but just there was yeah, there was for sure glycogen there. But since you talked about keto now, so for me, since I'm thinking a lot about all this in the context of keto as much as I can. I think it's
sure.
when it comes to metabolism, I think that maybe talking about a keto diet with a high metabolic rate in the same sentence or context, it's a bit incompatible. And I've seen a few people on Twitter where they do eat 3,000 plus calories by doing a keto diet, mostly the diet that Amber advocates for. Uh, but most of the people who eat maybe more protein and they're lean, probably they don't have metabolic problems, etc. I think they're
Right.
more below 2,000 calories.
Yeah, yeah, yeah.
And because it's satiating, they do 1 meal a day, maybe 2 meals a day. And at the end, I don't know if in that context, they can actually reach 3,000 calories or 4,000 calories. And how would they reach that? I mean, it's for me, it's pretty difficult to imagine one eating
You have to
four steaks.
you have to eat
Yeah,
yeah, you have to eat a lot of
you
a
need to
lot
take
of
care of yourself, right?
have to
So
eat a lot of chicken breast. You have to eat a lot of lean chicken breast to get to 4,000 calories. More than I can stomach, that's for sure.
yeah, exactly. So what do you think about metabolic rate in that context, in a keto context? Because I think actually maybe it's a little of an issue. So if you maybe metabolic rate is king, and then you try to fix your macros to fit exactly how you can properly digest, I don't know, 3,000 calories.
I don't know if there's anything wrong with if you're uh, a human who's eating, you know, let's say 2,500 calories a day of steak. I don't know that there's anything particularly wrong
If
with
it's
it. I think,
1,500, does
yeah,
that?
maybe it's 1,500. I don't know. I don't know what the number is, but that's pretty, right? That is a pretty low I mean, if you're really doing 1,500 calories of just steak or something, that's a very low metabolic rate for a human. Is that bad? I don't know. I know that humans have the capacity to have a much higher metabolic rate than that. Clearly, there's a lot of examples of it. The Tsimane forager farmers who live in Bolivia, like I say, they eat mostly cassava and rice, and they have a metabolic rate that's 30% higher than an American of the same if you do a body scan and you say, well, this is their muscle mass, this is their fat mass, you match them up exactly with the Tsimani forager farmers, they have 30% higher metabolic rate. And that's just resting metabolic rate. That's not while they're exercising or anything like that. That's just sitting in a chair. And so we see that the metabolism has tremendous capacity to go up or down based on the context, you know. And I believe that the fastest metabolisms that I've seen clocked are people like the Tsimani or rice farmers in Thailand that are eating these very high starch, very high carb diets, right? That seems to be that the carbs can goose the metabolism in a way. If you're good, but the catch is if you're burning the carbohydrates oxidatively in your mitochondria, and that is the rub because in metabolic syndrome, you can't do that. What happens is we have elevated levels of PDK, pyruvate dehydrogenase kinase, and what it does is it blocks the step where the glucose comes in, it goes through a process called glycolysis, it becomes pyruvate. The pyruvate shuttles into the mitochondria, and that's when you generate ATP from it. If you have elevated PDK, the enzyme that the final enzyme pyruvate dehydrogenase that essentially enters the pyruvate into the TCA cycle to get burned, that enzyme becomes inactivated. And then none of the glucose can get all the way into your mitochondria to get burned, and instead it gets used for anabolic purposes. And that step of pyruvate entering into the mitochondria is essentially the the place where people get dysregulated and you're no longer capable of burning glucose oxidatively.
So how? Let's dive into how you get fat, because you mentioned olive oil. I guess you'll mention PUFA as well.
So if we believe that uh, this we're in this state of subclinical hibernation, right? And that's the state that we're in. That's why we're using the glucose to build fuel, to build fat, rather than allowing it to burn, right? Then we have to start to think about I'm an evolutionary biologist, right? And so now I think, well, how did we get here, right? What are mammals? What are animals? What are the signals in our environment? Because if you go back to the dawn of mammals, when mammals first evolved, you had to know, the analogy I use in my article is a woodchuck and a rabbit, right? Because woodchucks and rabbits are very similar animals. They're both rodents. They both inhabit the same niche. Like they literally both live in my lawn. They both eat grass. They're both hindgut fermenters, and they're both rodents, right? So a lot of things are very metabolic, or their lifestyle, their diet, the temperature, the day length is all the same. And rabbits are extraordinarily lean, and woodchucks are extraordinarily fat. And the woodchuck is a hibernating animal, right? And so the woodchuck has taken up this lifestyle of fatten up in the summer, sleep through winter. The rabbit remains lean and survives through the winter by eating the bark off of saplings and buds and other things that it can get access to. And so the question is why? What's metabolically different about them? How did they choose that? And then of course there are other animal species who are somewhere in the middle of the woodchuck and the rabbit, right? And so what are the signals that that they can glean? Like how does a baby woodchuck who's born in June in New York State, it's very, very warm, the days are long, everything seems fine. How does that baby woodchuck know that winter is coming and that it needs to fatten up, right? And it's looking for signals. And so the most obvious one is day length. And of course, day length is part of this signaling. You can in the lab, if you take a certain type of squirrel and you put it into a room and you leave the lights on for 8 hours and off for 16 hours, that squirrel will get more fat than the squirrel in the room next door where the lights are on for 16 hours and off for 8 hours, right? So to some extent, we can control the fattening just with day length, but there's more signals than that, right? And so my I'm one of the few people online who are arguing against avocados and olive oil, and the reason is that I think another signal is that um, if you look at insects, right, the first mammals we believe ate insects, and so near the equator, if you look at ants, there's a study with ants in Brazil and ants in Germany, and the ants in Brazil are made of 30% monounsaturated fat. The ants in Germany are made of 80% monounsaturated fat. And so another signal, if you're a mammal, of do I live in the equator, do I live in the land of eternal summer, or is winter coming and I need to fatten up, is this incoming monounsaturated fat from the ants. Right. And so that's another environmental signal. But then there's also things, so glucose is most common, glucose is made while the sun is shining, and so I think all the way back, you're in a marine environment, right? That because ultimately we came from a marine environment. Um, the algae is the primary producer in marine environments, and it's highest in glucose and starch when the sun is shining and it's doing photosynthesis and it's building its glucose reserve. So at the end of a long sunny day, um, that algae is full of carbohydrate in a way that it's not going to be um, in winter in low light environments. And so carbohydrates are an ancient signal that the sun is shining, it's summer, things are good, right? And and there's a ton of examples like this. Another thing, these enzyme systems. I talk a lot about the aryl hydrocarbon receptor, and the polyphenols in plants will block the activity of the AHR. That AHR is part of the signaling that winter's coming. It controls your circadian rhythms and all these things. Um, and it's like it's saying, okay, winter's coming, fatten up. But if you eat enough polyphenols, which i.e., if algae is growing, there's lots of algae around, it blocks the AHR. And so that's another kind of summary signal are the polyphenols in the plants. And so that's kind of uh, how I think about the scenario, and what I've said in articles I posted this last weekend. Um, I'm coming around to what are the actual biological functions of linoleic acid and linolenic acid, the two polyunsaturated fats that are in plants, right? So people tend to think of them as being pretty inert unless they oxidize, and then they become these oxidized lipids. And people think that the oxidized lipids are bad. That's, I think, how most people think of the scenario. I don't think that's right. I think that um, it's complicated, but what happens is those PUFA, that linoleic acid, is involved in a an oxidative fermentation, right? So single-celled organisms, if they're in a low oxygen environment, what they do is they take in glucose, they do glycolysis, they make some ATP out of it, and then and the problem with that is it generates two molecules of NADH inside of the bacteria, and the NADH is an electron carrier, right? It goes from NAD or NAD plus when it doesn't have the electrons to NADH when it does have the electrons, and those electrons have to go somewhere. And so what you can do is you can stick it back onto the two molecules of pyruvate that you got out of glycolysis, and you can eject it as lactate, right? And then you can keep your metabolism going because as you're using glycolysis to make ATP, this NADH, this byproduct that keeps building up, you're sticking it back onto the pyruvate and you're getting rid of it, right? That's a fermentation. That's how we make sauerkraut, right? What the sauerkraut gets acidic because the bacteria in there are doing a lactic fermentation, right? They're taking the sugar um, out of the cabbage and they're converting it to lactic acid. And of course, when you make sauerkraut, uh, you put a lid over it so that no oxygen can get in, right? Because you do glycolysis in low oxygen situations, and that makes the lactic acid. Um, Yeast, they have the same problem. Except instead of producing lactate and exporting it, they ferment to ethanol and they export that, right? Um, but animals have a problem where you don't want to, if you need to do glycolysis, um, which you do in any kind of if oxygen is limited, and this is a situation that early animals had to deal with because there was not oxygen and not much oxygen in the environment. And so if you have to do this fermentation, you can't, now you're multicellular. Whatever you export out of your cells is going to go into the intracellular space, right? You can't do glycolysis and export lactate because you'll die of lactic acidosis. You're going to have similar problems if you ferment the glucose into ethanol and export that, right? That's not going to work in a multicellular animal. So what is there left? Um, Linoleic acid. So there's two desaturase enzymes, D6D and D5D. And what they do is they add double bonds to linoleic acid and they convert it to arachidonic acid. And each of those steps, the delta 6 desaturase and the delta 5 desaturase, both take the electrons from NADH and it gets stuck onto the polyunsaturated fat. And then that fat is less immediately toxic. Arachidonic acid is less immediately toxic than um, lactic acid or ethanol. And so the cells can ferment the linoleic acid and export it, and it eventually works its way and is excreted by the animal. And so that is the solution that animals chose for the NADH problem. And it runs through linoleic acid and linolenic acid that are, respectively in soybean oil and flaxseed oil. Um, and so these polyunsaturated fats are not inert. They're used to drive glycolysis. And glycolysis, as I've said, is fundamentally anabolic. And so the polyunsaturated fats are fuel for your fat tissues and for your liver to stay in this anabolic glycolytic state. And if you limit those PUFAs, they can't get as glycolytic. And just to bring all these things home, we'll go back to the squirrel analogy. When you look at an acorn is the an acorn was evolved by the oak trees to keep squirrels alive, right? It's sort of a perfectly fattening food because as the climate changes, as the glaciers come and recede, the oak trees have to migrate north and south. And the way that they do that is that the squirrels take the acorns and hide them places, and that helps the acorn disperse its nuts, right? And so it has to keep the squirrels alive, and so it's evolved the perfect uh, fattening food, right? And acorns are they have a lot of starch and they have a lot of monounsaturated fats, and they also have a significant amount of the polyunsaturated fats, not nearly as much as the monounsaturated fats. Because as I've said, the main trigger for all of this is the monounsaturated fat, but the polyunsaturated fats are needed as fuel to maintain the glycolytic state, and so and once that state is triggered, of course, then the starch is no longer being used oxidatively; it's being used glycolytically, right? And so that acorn, the starch, the monounsaturated fat, and the polyunsaturated fat has all of the things required to uh, induce that hibernation state. The monounsaturated fat is the trigger, and the starch and the polyunsaturated fats are the fuels to do that glycolytic anabolic behavior.
Mhm.
And it's pretty swampy, of course.
Thanks for the explanation. Really, really enjoyed that. What is this the same in the keto context? So if someone, because now we said starch, we said glucose, so we remove glucose at least from the diet, but we still have in our diet linoleic acid, olive oil, for example, monounsaturated fats. Do we still end up with the same problem?
So I think as long as you intend to stay in a ketogenic state forever, I think it's probably fine. If you don't have that, if you just continue to avoid the carbohydrates that are fueling this process, it's probably fine. Uh, However, I think that like I say, a lot of biology is about locking in the state of the organism. And one of the ways that the organism locks in that subclinical hibernation state is that you have increasing amounts of monounsaturated fats. So I use it as example, um, the the fat-tailed dwarf lemur, right? The primate who hibernates through the dry season in the summer in the tropics, right? Um, and if you look at that lemur, uh, its body fat is like when it's fattening is like 70% oleic acid, right? The same fat that's in olive oil. And so one of the and there's a transcription factor called SREB-P, and it's activated. Oleic acid binds to it and activates it, and it controls the lipogenic process, which means fat making, right? And so one of the ways that the state of the organism is locked into this hibernating torpid state is the rise in your levels of oleic acid. It binds SREB-P. It's in 10 different ways. It's part of this positive feedback loop, right? Because that's how the animal knows, your fat. Think about this. Um, your muscles and the glycogen in your liver, those kind of are what they are. They have to be made the way that they're made. You can't really change them, right? If the organism needs a way to save the state, you know what I mean? Like, is winter coming or not? That's the question, right? And one of the ways it locks in winter's coming, fatten up, is by the fat composition in your adipose tissues. And so when that gets really high in oleic acid, as it will if you're consuming significant olive oil on a ketogenic diet, when you try to switch back to carbs, it's going to be very hard to do because the oleic acid is telling the organism winter's coming, fatten up. So no. So it's if you're fine to remain keto forever and you want to enjoy olive oil and olives, I think that's fine. But it's just going to make it harder when you try to get out.
And so there are two things that well, let's start with the easy one. So I'm Greek, now I'm in Greece, you know. I have
Sure.
my
Yeah.
garden. Actually, if you look at just here, 20 meters from me, I have actually planted myself around 40 olive trees.
Yeah.
So
Yeah. Yeah.
for little guys, now they're grew, and I'm really proud of them. But should
Yeah.
we
Yeah.
consume them or not?
Well, it's right. So, one of the reasons that I'm sort of loud on this topic of avoid olive oil is that no one else is talking about it, right? And so I'm trying to generate discussion. I think there are other states. If you're reasonably healthy, and you can use olive like there's a lot of evidence that people absolutely can remain healthy consuming olive oil, right? What I've noticed, and I think is interesting, and I've never been to Italy, I've never been to Greece, that I know that and maybe you can enlighten me on this. Like I know that the traditional Italian meal sequence is that you eat the carbohydrates first, like you would eat the pasta first, and then later in the meal you would eat the meat. That's very interesting to me because it suggests that um, I believe that olive oil creates and it happens because you eat the olive oil, you produce this thing called OEA, which triggers PPAR alpha, which PPAR alpha controls the switch into hibernation, right? And the olive oil triggers that. It doesn't trigger it very strongly, it just triggers it a little bit, but it's measurable in humans. So if you feed a human bread and butter versus bread and olive oil, um, an hour after that meal, the human who ate the bread and butter is going to be burning more carbohydrates than the human who ate the bread and olive oil, because the olive oil is causing mild but acute insulin resistance. And so, um, for some people, that's fine, but I think that's why in the Italian meal, they eat the carbohydrate first, because the olive oil is going to make them insulin resistant. So you want to generate a big insulin response. So you eat the carbohydrates before you eat the meal so that you can get the branched chain amino acids down, and then you eat the steak. Right. To me, that looks like a strategy for dealing with the olive oil. And so, you have to think about it as sort of, but also, I assume there are other customs in Greece around the structure of the meals and the structure of the day, and of course, all of that is comes from thousands of years of people trying these things and noticing certain patterns and saying, okay, well, we do it this way for these reasons.
Well, I was actually reading about the Italian cuisine because because of the curiosity that the sugar diet triggered me, and that's why I was asking you about the meal timing and micronutrient separation, because it seems that in the army they were giving, like say this is First and Second World War, they were
Right.
giving either uh, as in a lunch or breakfast, 250 grams of apples, so carbs primarily, or
Right.
little amounts of sardines or little amounts of cheese. So they were never, I mean, they
What,
were
what was the last thing?
cheese.
Oh, okay, got it.
So, but they were not mixing stuff. So maybe this
Right.
goes, and what you said as an example, the primo, they have the pasta, and then the second plate, meat, for example, then they do keep it very strictly. In Greece, we don't have that so much, um, but I think we also have problems so with obesity and. But I have interviewed ladies like in their 80s, etc. And so how they were living in the islands like 50, 60 years
Mhm.
ago. And they were actually doing this mealtime separation. So they were not mixing things together. Uh,
Right. Interesting.
um, I'll dig it up because I don't remember it exactly, and I can share this with you. Okay, let's keep discussing this before we switch topics, because then again, do we have we seen research about how long olive oil or oleic acid or linoleic acid stay in the body? Because people typically, when they refer to linoleic acid, they say half-life of 2 years, and the extract loss also measures it, and it seems it takes a while now. So, um, what's happening?
Yeah. So it's very different the way that the two fats behave, right? So your um, and I wrote an article on Sunday, then published it on my blog. I think it's called "Can You Stand in the Same Cell Membrane Twice?" Um, what happens is the linoleic acid only comes from your diet, right? So if you stop eating linoleic acid, the amount of linoleic acid in your adipose tissue is going to go down over time. Um, and the linoleic acid is actually stored preferentially. Um, I think people think about cell membranes as and cells in general as kind of static things, when in fact they're very dynamic and they're constantly being recycled and replaced. And one of the things that happens in your cell membranes is that um, you're constantly swapping out. There's two each fat that's in the cell membrane has a little water soluble part. That's the phospho. When we say phospholipid, that's the phospho part is water soluble, and then the two fats stick down into the fatty membrane.
Mhm.
And there's two fats here, and one of them is constantly being released by an enzyme called LPA2, and it's being replaced by another enzyme called LPCAT3. Um, and the one that is always there, SN1, that's anchored in the membrane, is typically a saturated fat. And this one that's being replaced, the enzyme that does that heavily prefers linoleic acid. And so the linoleic acid is being used in this second position, and it's being used for the reasons I said before, that if the cells need to quick jump into glycolysis, they have this buffer of linoleic acid all around them that they can use to regenerate NAD for glycolysis if oxygen becomes limiting. Um, and so for that reason, what you see is that in people with metabolic syndrome, they tend to actually have lower levels of linoleic acid in their adipose tissue compared to the average person. Now, there's a lot of variables here, right? So as people have eaten more seed oils over time, on average, our levels of linoleic acid in our adipose tissues have increased, right? 100 years ago, it might have been 10%. Today, it's more likely to be 20 to 30%, right? But if you look at the population as a whole, the people who are metabolically healthy might have 25% linoleic acid in their adipose tissues, and the people who are metabolically unhealthy might have 18%, right? And so that seems ironic because people will say, because some people are saying, well, seed oils are bad, they oxidize and they cause this inflammation. And other people are saying, well, then how can you explain the fact that the metabolically unhealthy people have less linoleic acid, right? And to solve that question, we have to realize what the fundamental use of the linoleic acid is. And I'm arguing that the fundamental use of the linoleic acid is this glycolytic anabolic. It's fueling this glycolytic anabolic system, right? And so yes, if you stop eating the seed oils over time, your adipose tissues levels of linoleic acid will go down, and this takes a couple of years. Also, if you're metabolically unhealthy, what's happening is that system that does de novo lipogenesis, its main product is oleic acid. So, and that's part of that positive feedback loop that, like I say, once you enter into subclinical hibernation, you switch on PPA or alpha. PPA or alpha is causing you to do a lot of de novo lipogenesis, and the end product of that is oleic acid. So you can't clear the oleic acid. The only way to reduce the level of oleic acid is to reduce the amount of de novo lipogenesis that you're doing. You have to stop triggering this system that is putting you into this state of subclinical torpor, right? And over time, hopefully, your stearic acid levels, right? So stearic acid, the steps are like this. DNL creates palmitic acid, which is a 16 carbon saturated fat. The palmitic acid is relatively stable. It tends to build up, but a small percentage of it, there's an enzyme called an elongase, which sticks another acetyl group on it, and it now becomes the 18 carbon saturated fat stearic acid. And there's another enzyme, SCD1, which is a desaturase, which converts it to oleic acid. And so what happens is when you're doing a lot of lipogenesis, you see elevated palmitic acid and elevated oleic acid, and then stearic acid goes down and linoleic acid goes down. That is an unmistakable pattern. I've seen it in 1,000 papers. And it is the pattern of de novo lipogenesis. And then that pattern locks you into that state because the elevated oleic acid activates SREB-P1C, the lipogenic master controller. And so the only way to lower the level of oleic acid is you have to somehow break out of this pattern, right? And that is sort of what my blog is about, and we're trying to figure that out. where can we block that feedback loop?
So first, before we, because I would like to give maybe some practical tips to everyone listening. But first of all, from what you said, is that eating more, so what I kind of brought up before, to increase your metabolic rate probably might make the problem worse if
Right.
basically you give if you don't change the signals in the environment. Either that's light
Yes.
or it's oleic acid or whatsoever. So you need first to change the signals and then
Right.
slowly start adding calories and getting out of that
Yeah.
torpor. So it's both go hand in hand. So adding calories just in the same type of diet then would not get you out of torpor. Basically, you just get you
Right.
more fats.
Right. Yeah. That's what I think. And yeah, and like you say, it all, vitamin D competes for. So I've said that PPAR alpha is the master controller of this subclinical hibernation. Well, PPAR alpha and vitamin D, they both need a binding partner before they can have their effects. And they're actually competing for the same binding partner, which is RXR, the retinoid X receptor. And so in summer, if you're getting a lot of light, you're generating a lot of vitamin D, that's one way that you can compete with this subclinical torpor, right? That's another, obviously, light is a summer signal. The vitamin D competes directly with PPAR alpha. The oleic acid activates the dietary oleic acid, especially activates the PPAR alpha. And so they're kind of in opposition of each other. Right. And I think here's another way that people uh, get misled, let's say, right? It's not really their fault. It's that we say, you know, saturated fat means butter, steak, and pork, right? But the reality is the butter is 70% saturated. The beef is maybe 50% saturated. The pork is more like 38% saturated. And so, if people are like, well, I'll eat I'll eat bread with lard. Well, lard is mostly monounsaturated. Lard is a lot closer to olive oil than it is to butter. Um, and the same with egg yolks, although eggs are a very nutritious food and egg yolks don't have that much fat in them, but egg yolks are another source that is very high in monounsaturated fat. Chicken fat is very monounsaturated based. And so there's a confusion about what saturated fat really is and right, the dairy products are going to keep you much closer to the right dairy. Here's another way to think about it. The fat produced when you do de novo lipogenesis, the content of it looks a lot like lard, honestly. Except although lard is higher in stearic acid than human fat, so that's a benefit of lard. But that's why in the mice studies they use lard. It's lard spiked with a little bit of soybean oil to give it some extra PUFA. But those diets that fatten up the mice are lard based, right? And so we shouldn't equate beef fat with butter fat necessarily. I don't think. I don't. To me, they're very different sources of fat. The butter is about 20% monounsaturated fat, and I think if it's grass-fed butter, it's maybe even less. And so butter doesn't have a lot of that signal that activates the PPR alpha, although some of the kind of medium chain fats do. But and butter has some of those, but it's less than to me, it's the most beneficial of all the fats. And obviously uh, entire cultures have shown for 10,000 years now that combining butter and starch can work if you're metabolically healthy, right? We know that.
Hmm. So just to nail the point or your point for oleic acid. So the body, in any case, transforms when it's doing de novo lipogenesis, some part of that stearic acid or palmitic acid into oleic acid. So the body,
Yeah.
in that state, creates monounsaturated fat. But the process of eating our cells monounsaturated fats more, then gives an extra burden to the system, or to it
It
creates.
does.
Okay.
Yeah, we know the mechanism by which that works. When you eat uh, oleic acid, it generates a molecule called OEA, oleoyl ethanolamide, and that thing is a very potent activator of PPAR alpha. And you can see in human feeding trials, like I say, you do butter. This person eats bread and butter. This person eats olive oil and butter. The person that eats the bread and butter every time will oxidize more of the glucose from the meal than the person who eats olive oil. And the people who support olive oil say olive oil helps you burn fat. But in my opinion, that's not the right way to burn that meal. If you eat bread and butter, you actually want to burn the carbohydrate first, and the olive oil reverses that.
Okay. In your recent blog, you also say, switching a bit topic, but maybe it's related as well, that there is this glycolytic switch is the activation of macrophages, you say. And macrophages or immune cells
Yes.
rely on oxidative phosphorylation, etc., etc. And that sounds very interesting. So macrophages is inflammation, is heart attack
Yeah.
problems. So
So yeah. So I use the example of the macrophages. Right. What I'm trying to do in this series of articles is use uh, simple examples that we see that have been proven in the lab that people are familiar with to make these points about the kind of fundamental metabolic state of cells. So classic example in the lab is the activation of macrophages. And so of course macrophages are immune cells and they run through your bloodstream and they're in your tissues, and um, they're looking for invaders. They're looking for bacteria, mostly. They're looking for cells that have got viruses, and they have these receptors. The macrophages do not rely on um, things like antibodies, right? They don't, a macrophage doesn't recognize a specific bacterial species. It recognizes bacteria sort of in general. It has these receptors called TLR, toll-like receptors, and bacteria have these specific glycolated proteins on the outside of them, and the macrophage sees one and says, "Uh-oh, this is not supposed to be here," and that triggers this cascade of events. And what happens is, to fight off the invader, the macrophage has to become very anabolic, right? And so I'm arguing essentially that um, the switch, the macrophage becoming glycolytic, is the same state that your fat cells are in. The outcome is different because the job of the macrophage is to kill intruders. The job of your fat cells obviously is to store fat. And so if you trigger this anabolic state and the macrophage, what it's going to do is it's going to become very glycolytic. It's going to increase its metabolic rate, and it's essentially going to crank out a continuous stream of superoxide, these reactive oxygen species, and that superoxide will kill the bacteria. What it's also going to do is it's going to increase the size of its membranes, and it's going to phagocytose these bacteria. And so the macrophage can increase in size by like tenfold um,
um,
when there's an invasion, and they have to keep eating these bacteria. And so it's a very anabolic state that the macrophages switch into, right? Um, and I talk about the specific uh, proteins. Uh, they're not really enzymes; they're transcription factors, which control other enzymes. But I talk about the specific transcription factors that are responsible for turning on that glycolytic transition in macrophages. And the thing is, all of those transcription factors are also activated in the adipose tissue of obese humans, right? And so we can see these underlying fundamental processes that control the state of the cell, right? The context of the cell. Like, is this cell fundamentally anabolic or catabolic, is controlled by NRF2, NFKB, NF kappa B, I think it's supposed to be pronounced, PPAR alpha, and I'm forgetting the other one. but but that pattern is unmistakable, right? It's like, okay, you have activated macrophages, you see those four things kick in. Okay, you see the fat tissue and obesity, you see those four things kick in. Um, and so, the this latest series on the blog is really about, it's called the whistle pig in the hair, by the way. Back to the woodchuck, and the whistle pig is a country term in the US for woodchucks, which I think is funny. But the new series of articles is about this kind of fundamental nature of the cells, that it has to do with oxygen, and how do the cells know what they're doing? Are they anabolic or are they catabolic? And what are the factors that control that fundamental state, right? And that's really what we're drilling down into, and how are the different fats involved in that, and how do we control the flow of oxygen and therefore electrons through the system, right?
So what are the practical tips for someone to start reversing that state?
Yeah, so well, I mean, it's a lot of the things that we've been talking about, right? You don't want to, um, you know, it- you can look at these mouse models, right? Let's go back to that, and you can see that certain patterns, like I say, I've been making this. Here's a good analogy, right? Let's say you're an American mother and you're just trying to feed your kids, and you're concerned about their health, but you need something that's convenient, and the kids are picky and they only eat a few foods. And so you're like, all right, listen, I'm gonna feed these kids macaroni and cheese because it's the only thing they'll eat, right? But I'm health conscious, and so instead of putting butter into the macaroni and cheese, I'm going to put olive oil in it. And also, I'm going to make them eat a vegetable. So I'm going to give them a salad, and I'm going to put Russian dressing on it because I know they'll eat the Russian dressing, right? And in the US, Kraft Russian dressing is made with polyunsaturated fat. And then you feed that to your kids. What did you just do? You just recreated the exact fat blend that we use in the lab to produce diet-induced obesity in mice every time, right? The cheese is bringing in the palmitic acid from the lard, the olive oil is bringing in the oleic acid from the lard, and the salad dressing is bringing in the polyunsaturated fat that comes from partially from the lard and also from the little bit of soybean oil that they spike into that mixture, right? And so people are trying to be more healthy by adding these new sources of polyunsaturated fat that weren't in the diet, 50 years ago. Um, and so I just think that, everybody's going to respond differently to different things, right? And if you are metabolically broken, different people are metabolically broken in different ways. But, I think that's where you can start, if you're doing your own self-experimentation, you could, right, you have to think about the different types of fats in addition to thinking about, sure, maybe protein restriction is helpful for you. Maybe it's carbohydrate restriction, maybe it's fat restriction altogether. But I think I think the more fundamental understanding that we have, the more you can develop different strategies and try different things. And I think that's really
So for
where the
me,
blog is going. So I would say do not combine different sources of fat in the same meal. If you're going to eat a fat, just stick with that one. And when you think about fat in the context of a meal, right? You can think about it in of course, in terms of your overall diet as well, but in that meal, um, the free fatty acids that cells have available to them, right? So I said that the membranes are very active, right? They're constantly replacing the fats in that SN2 position. And that is a fundamental controller of this glycolytic anabolic state. And so if you eat this specific meal, that is butter, olive oil, and salad dressing, soybean oil, the olive oil is the thing that triggers the whole system, the PPAR alpha, right? So the olive oil is triggering the thing, but it's driven forward by the uh, polyunsaturated fats that you ate in the same meal. And so those polyunsaturated fats are going to be high in your bloodstream, high in your free fatty acids because you just ate them and their fuel there. And so you in that one meal, you've introduced the trigger, which is the OEA, and you've introduced the fuel for the ongoing glycolysis, which are the polyunsaturated fats. Right. And so and that's why the diet works so well in the lab for the mice is you've given them everything that they need, as well as the starch, right? The starch is used for the glycolysis. And so, any way that you can sort of move away from that look. And I'll say this too. There are, you know, in mice studies, up to a certain extent, there's evidence that you can sort of feed them starch and like high linoleic safflower oil, right, which is very high in polyunsaturated fat, but it lacks the monounsaturated fat and the palmitic acid. The diet of starch and safflower oil doesn't provide the full suite of things to truly click on that, that.
We have three components. So I'm hearing carbs or starch is the fuel, oleic acid is the trigger, and polyunsaturated fats or the mediator, sort of.
Yeah, exactly.
So
Yeah, that's essentially exactly how I think about it.
I asked about the practical tips because I think we need to kind of start from the base, right? So have a proper foundation. So maybe I'm not sure if one should say protein restrict to 5%, but keep protein, let's say, at a medium level, not overdo it. I would add already get more sun, and then try to stick to saturated fat primarily as your fat source. And then if you want to
Yeah,
go keto, do that. If you want to add some starch, do that. But then that's kind of the foundation without going too much in the rabbit hole because what you said, people need to understand. Yeah. And if,
right, absolutely.
but then you start to introduce some concepts as well, which are for me new for me as well in your blog, and you start mentioning about the glutathione. You also talk about excessive or chronic supplementation of vitamin C and vitamin E can be create insulin resistance.
Yeah,
There are a lot of little things. So one might be taking, for example, vitamin C because he heard that he has a high LPA and he heard that this is
yeah.
good for his heart, for example, right? So there's a billion
Well,
other.
and a, a lot of people take vitamin E as well, and think that vitamin E is very good.
Yeah.
And I think that's an important piece. The other piece is right. So I think the antioxidants are dangerous. You know, we are oxidative creatures, right? We burn our fuel. So if you're taking antioxidants, that's sort of fundamentally against the nature of metabolism, right? It's right there in the name. The whole point is we want to oxidize our fuels, and so you take antioxidants. Well, that's you're shooting yourself in the foot. And then the other problem is this: the environmental toxins, right? And so I just went to a chromatography conference about PFAS, PFAS. These are polyfluorinated something. This is like Teflon, nonstick coatings, right? A lot of these have been eliminated, but in the US, anyways, we have not found a single person who doesn't have a measurable amount of these polyfluorinated compounds, and they look very much like fat. It's a carbon backbone, but instead of hydrogen atoms, it has fluorine atoms, and so it looks like It looks like fat to the body, and these things activate PPAR alpha. So perhaps in a world before these key fasts were in everyone, the issues with oleic acid wouldn't be such a big deal. But now you have all these other activators of PPAR alpha.
Hmm.
Another one is the phthalates in plastics. right? And now all of our bloodstreams are full of microplastics. And so, don't eat things that are wrapped in plastic. That's a problem for a lot of carnivores because meat comes, at least in the US, meat comes wrapped in plastic, right? Um, Microwaving things in plastic. These are things that are hard to, um, avoiding plastic is really hard. All of our food comes wrapped in plastic. Um, and the PFAS are in your drinking water. Probably the microplastics are too. Um, and so these are other things to think about is how can you reduce your exposure to plastics? Um, Maybe filter your water to get the PFAS out. That's something I should do. I don't do it, but I should. I should have a water filter. You know, uh, all of these things are contributing, right? And so yeah,
Yes, it's the whole environment actually, right? So it's not
yeah,
we live in a pretty yeah strange world. I don't know what's the right
yeah, yeah.
word for that. What do you think about exercise? So just to completely change topic, but is exercise a trigger of I don't know.
So, I think exercise is really good. Um, in my experience, there have been several times in my life when, I was overweight. Um, I mean, I still am overweight, but I'm losing weight now again, and it's good. But like, there's several times in my life I've tried to get my weight back into the normal range just by exercising, right? And I've never lost a single pound that way. Like it just doesn't work. Um, if I don't do something dietarily, I will not lose weight, and it doesn't matter uh, that I'm now exercising and running and lifting weights and all these things. It just doesn't move the needle for me.
So
So I don't emphasize this a lot.
I didn't ask you because of calories you burn, you burn more calories or whatsoever. I think that's kind of proven that doesn't work. I wasn't aware if there are any effects of exercise on PPR alpha or on all these
You know, I don't see it personally. I haven't looked more. I haven't probably looked specifically at the relationship between exercise and PPR alpha, but it's just been my experience that, as someone with that has struggled with overweight my whole lifetime, I have never seen a time when I thought that. I mean, in high school, when I was on the wrestling team and we were having like vigorous 2 hour long essentially like the level of training, if you're a high school or college athlete, if you do that much exercise, it probably has some benefits, but most of us don't have
yeah yeah.
that much time in our busy lives to devote to, you know,
Actually, intense exercise. I mean, I will need to look up the studies, but they actually tend to drop metabolic rate, or maybe they drop, fidgeting, etc., because you're just so tired and you just lay on bed or on the chair and don't.
right. Yeah. Yeah. Yeah.
Yeah,
Yeah. Well, and I'm a guy, I'm like, it's hard. Like, you can see me moving around a lot in my chair. It's hard for me to sit down and talk this long. Like I'm kind of a frenetic guy. I pace around and I played I haven't done it in the last year since I moved to Buffalo, but my whole adult life I played competitive basketball. Um, and so in the context of someone who's constantly pacing and playing competitive basketball, you know, I was still fat. And so, it's like obviously that I'm like and I was running a farm, I was running a farm, so I was out in the fields running after the pigs, picking up stuff, carrying stuff, and um none of that helped me stay lean, right? Like so if exercise is a way to stay lean, I,
no,
I was getting a lot of exercise.
no, I agree. It has a lot of benefits, but then maybe not in that context. Just looking at my notes, I want to circle back on calorie restriction, or actually we said metabolic rate, calorie restriction, and longevity? Because you actually said that maybe actually in the keto context, having a lower metabolic rate, I mean, we don't know. Maybe it's okay. And I saw a few very recent posts of certain researchers saying that if you reduce the calories by 65%, the mice live the longest we have ever seen. So, and the calorie
Yeah,
restriction is the strongest tool we have for longevity at the moment, far beyond any pharmaceuticals or whatsoever. And this makes you really wonder, actually, in the context of this discussion we're having. I would advocate that we need, yeah, and I think you do as well. We need to eat a lot of calories. So
yeah,
at least the studies say that if you eat less, the mice live longer.
yeah. I mean, I think that's one. We don't know if in humans if calorie restriction actually extends lifetime, right? We see evidence of this in things like mice, and I think in things like fruit flies. But of course, mice and fruit flies are very short-lived. A lifetime for a mouse is perhaps 2 years. I think they don't live a tremendous amount of time. So in a very short-lived species, mice have a very high metabolic rate. It's something like pound per pound, their metabolic rate is 12 times as high as humans are, right? And so that's nice in the lab because it's easy to show uh, you know, this supplement or changing the protein a little bit, you see that effect in the mouse because their metabolic rate is so fast that they change very quickly. So it's a nice model for seeing the little differences that a protein or a fat makes, right? Um, Having said all that, I'm not sure if calorie restriction extends the life of a mouse, which is an incredibly high metabolic rate, short lifetime thing. How does that translate to humans? I don't, who can say? It's going to take a while to find out.
Oh, but what's your gut feeling? Because I think for me, very simplistically, I think we need energy to heal. We think we need
Yeah,
energy.
I mean, I agree. I don't, right? I don't expect to live forever. And I would just like to be healthy and happy in the time that I'm here, right? And so for me, that's about um enjoying the foods that I eat, and it's about yeah, I want to have a high metabolic rate and dance and do the things that metabolically healthy humans do. That's my priority versus longevity per se.
Okay. What's your priority now in the lab? So what is the tests that you're actually now doing or you will be immediately doing?
So the goal of the lab is to essentially I want to map out how the electrons move through the cells and which enzymes, which transcription factors control that process. How does it work, and how the different things that we feed the cells change that process? So, um, we've been talking about the interacting effects of oleic acid and linoleic acid. So now what we can do is we can run. We have dishes that are running human liver cells, let's say, and we can alter the amount of oleic acid and linoleic acid, and we can do this in as many replicates as we want. We can do, you know, 80%, 20%, and 75, 25, and 70, 30, all the way down the line, right? And then what we can do, we can use fluorescent dyes to tell us how did the NADH to NAD plus ratio change, right? Because the NADH holds the electrons. We can say, how did the NADPH to NADP ratio change? Because the NADPH holds the electrons. We can say, how does it affect fat accumulation? How does it how does it affect ROS production? How does it, and then we can do things like I mentioned in the blog, um, one of the, you mentioned it, but I said that this thing called BSO blocks the formation of glutathione, which people call the body's master antioxidant, but that's not really true. Glutathione is the fuel for the enzyme glutathione peroxidase, which is the body's primary antioxidant enzyme. And so if block the production of glutathione in a mouse, they're protected from the diet-induced obesity. And so to me, that glutathione is a redox buffer that can be used for antioxidant defense, but can also be used to drive the fattening process because that compartment is fundamentally anabolic. And so these are the questions, right? So I could use something like that BSO and say, okay, do the oleic acid and the linoleic acid have the same effect in the same cells on NADPH to NAD plus ratio, ROS production, lipid accumulation, if you block production of glutathione, right? And then we can do the same thing. How does it work if we block PPAR alpha? And this can all be done with robots and automation, and so we can collect a tremendous amount of data in a very short period of time with the tools that we have. Just it does take money. That's the limiting factor. It takes money and time, right? Those are the limiting factors. But
So
we're getting there.
you're trying at the moment to get funding for running.
We are going to be, yes. I've announced I am in sort of partnership on this with Ashley Armstrong from Strong Sisters, and she's done great work in terms of one of the things she's doing is she raises eggs on her farm, and she's doing great experimental work on um, changing what uh, changing what she feeds the chickens and seeing how that affects the fat composition of the eggs, right? She's trying to create eggs with a healthier fat composition. And so now I can take those eggs in my lab and I can say, okay, here's here's regular egg you buy at the grocery store. Here's Ashley's eggs that she's put all this work into making the fat composition better. Now we can feed those two fats to the cells and see how it affects them, right? So we can feed them grass-fed butter versus you know, regular grocery store butter and see what effect that has. And all of these different foods. And I also have the machine. I bought a gas chromatograph so that we can take we can take food samples. And this is not live yet, but at some point, if anyone, this is a good way to fund the lab. If you're curious about the brand of olive oil you use or your farm's pork, you can send a sample to the lab, and for $100 or so, maybe it'll be $120. We can run that sample and tell you exactly what the composition is in the food that you're interested in. And then we'll be able to correlate that all back, of course, to our studies and show how it works in the cells, the liver cells, the adipose cells, and how that system all works. So, the idea is we're really trying to build this integrated system, thinking about how we produce foods, what are the different foods made out of, how do those changes in the foods affect actual human cells in a fundamental way.
Mhm. Can people literally try to support you? So is there a way that you?
Yeah, so not yet, but we will be announcing it. What I would say is check back in and fire in the bottle. Watch. I'm on Instagram, fire_bottle. Ashley Armstrong, Strong Sisters channels, and they'll have updates as well. I'm going to go on that show this in July, and we'll make our sort of official announcements. We haven't set up the mechanism yet for sort of donate here, and we need things like bank accounts and
Okay.
web pages and all these things built. We haven't done that yet, but we're working on it.
Many thanks, Brad. I really
Yeah, thank you very much.
you.
Yeah, of course.
Thank you very much. Take care.